today's session of AstroTalk. We are here to present today's talk on the topic called blue stragglers, which are the stars which are hot blue and luminous stars found in star clusters, specifically globular clusters and open clusters. They appears to be stragglers because they are bluer and brighter than the majority of stars in the clusters, which should have already evolved into the red giant. They seems young appearance for blue stragglers, while the rest of the cluster is old, which is a very puzzling and mysterious for the scientists who are trying to solve this uh, blue straggler mystery. Okay. However, there are so many things to learn from these blue straggler stars, which are present at present. Okay. Uh, UV ultraviolet light observation provide a unique and powerful tool to study these stars as they emit strongly in UV due to their high temperatures. So today's talk, we are going to find more details about this and findings and all. So with that, I would like to invite Mr. Dr. Gaurav Singh from uh, National Astronomical Observatory, Chinese Academy of Science, NAOC, where he is LUIT postdoctoral fellowship, and prior to that he has done his doctoral and other things from India. Aries, he was associated with Aries Research Institute of Observational Science, then Indian Institute of Astrophysics, Bangalore, and then for his postdoctoral fellowship where he has worked with the initially Indian Institute of Astrophysics, and then now currently where he is associated for National Astronomical Observatory, Chinese Academy of Sciences, Beijing, China. He has lot of recognitions, and as well as he has done his writings as well as publications. Okay, prior he has done his BSc, MSc from Banaras Hindu University, and then PhD in astronomy and astrophysics from University of Delhi. Okay, for he has attended a lot of talks, posters, and seminars on various topics. I can, if I start writing, it will take up a lot of where we are excited to know more about the blue straggler stars. But just to name few of them, I would say that there are a lot of science outreach, extracurricular activities where Gaurav Singh has interested, and then he has done almost couple of publications. Not couple of word is not a right word, but I would say more than 6 to 7 publications which are very prominent. And then also he has a lot of writings into the particular subject. So he's very much interested in this topic. Without taking much of the time, I would like to introduce Dr. Gaurav Singh for his topic on the blue straggler stars. Welcome to AstroTalk of Astronomer Association of Mumbai. Welcome, Gaurav Singh. Over to you.
Thank you very much, sir. I hope the slide is visible to all of you.
Yes, we can see it.
Okay, so thank you. So, very good evening, everyone. I am Gaurav Singh, working as a postdoctoral fellow at NAOC Beijing. So, I'm glad to have been given this opportunity to present my talk to the bunch of astronomy lovers here. And through my work, I've been involved in the studies of these formation of an exotic and unconventional group of stars. These are called blue straggler stars, and hence today's talk is titled "UV Clues to the Mysteries of Blue Straggler Stars," and I will try to give more insights into their origin, their formation mechanism, and some new discoveries. So, I'll first cover the star clusters. So blue straggler stars are basically found in mainly in the star clusters, and some are also found in the field regions. So the star clusters are basically categorized into two main categories. These are globular clusters. So in our galaxies, these globular clusters are found. So this is the schematic of the Milky Way. This is the galactic disk, and we have the galactic halo around that, and this is the galactic bulge region. So these globular clusters are found to be in the galactic halo and in the galactic bulge. They orbit this Milky Way in a elliptical orbit. So these globular clusters are very dense in the central region, with the typical stars are millions in numbers, and their density is very large. 10 power 4 to 10 power 6 star per PC cube. So they're very dense systems. So in our global galaxies, these globular clusters are found in 150 numbers, and these are not only limited to our galaxy. The globular cluster are found in nearly all the galaxies, like ultra diffuse dwarf galaxies, and we have nearby dwarf galaxies like LMCs, SMCs. So globular cluster are also found there. They also found in other spiral galaxies. In Andromeda, they are in 500 in numbers, and in some large ellipticals like M87, these are found in 10,000 numbers. So globular clusters are found at various different stellar systems. And the other classification of star cluster are open clusters. So these are this is the face view of our Milky Way. So these open clusters are basically lying close to the galactic disk. So they're lying over different scale height from the galactic disk. So they basically are another gravitational bound system, but they're not as dense as globular clusters. And this is a typical figure of an open cluster. So these blue straggler stars are basically first identified by Alan Sandage in 1953 in the external regions of galactic globular cluster M3. So these are found in the outer regions, and this is the HR diagram of galactic globular cluster M3. And you see these. This is the main sequence, and these are the giant branch, and we have horizontal branch, we have extreme horizontal branch over these sequences. So blue stragglers basically lie or they appear as an extension of the main sequence, or they are bluer and brighter than the this main sequence turn off. So why they are called blue stragglers? So basically, all the other stellar system, as we know from stellar evolutionary theory, when star is in the main sequence, they burn hydrogen. But as the hydrogen in the core get exhausted, it moves to the giant phase. While these stars still manage to survive at this location, indicating that these stars still burn hydrogen in their centers. So this is very puzzling, and this led to astronomers to think that these are not actually the part of the cluster members, because they occupy an unusual location. And till 1990s, when HST observations were possible, it was these blue stragglers were actually thought to be non-members. But after HST observations, they found in nearly all the globular clusters, and it was later confirmed that yes, they are the members. So now, with the membership, this was a problem that how to explain their origin. So how they are getting the extra fuel. So this was later being studied by various theoretical models and by observations. It is now established that there are three possible formation channels of the formation of the blue straggler stars. One is the collision, and this is a very possible collision mechanism where the density is large. So basically, in the centers of the galactic globular clusters and some dense stellar systems, these are where collision is very prominent. So there, blue stragglers are formed with the mergers of two stars. Where outer region of the globular cluster where binaries could survive, this mass transfer mechanism is very probable. So these blue stragglers are also known as vampire stars, and this is because they accrete the mass from their companion, which is in this case a giant branch, like subgiant or red giant or AGBs. So these giant branch, they transfer the mass to the blue stragglers, and this lead to formation of blue straggler from mass transfer channel. So there is another mechanism which is more theoretical, but very few observations of that has been confirmed till now, and that is only indicative. That is triple systems where blue stragglers are formed as a binary, but the mass transfer is actually coming from a tertiary companion, which is an outer binaries. What we need to do is to study different clusters and to really understand how these stars are formed and what are their evolution and other features. So, uh, as we have this globular cluster NGC 6838, these are the typical class of globular clusters where we have density is very large in the central region. So with the larger density, what happens is you have multiple interactions. So these are the various gravitational interactions happen. So central region is very dynamic. So star collide, they get relaxed. So basically two body relaxation happen in the central region and the outer region, but basically very prominent in the central region. So what happens with this is basically the binaries which are formed in the central region are basically disrupted by the stars which interact with them. So like this is the case where these are the binaries which are primordial binaries, the tertiary component interact with it, and this makes the original primordial component get separated, and this is what we have a formation with collision of the blue straggler star via collision formation or merger scenario. But when we move to the outer region where binaries could survive, there we have the binary formation mechanism or mass transfer channels. So this is the star in a giant phase. So blue straggler star accrete the mass from it, and it gets bluer and brighter. And this star either evolves towards white dwarf, since the envelope doesn't have that mass to go to the further evolution. So it settles as a white dwarf, either as a helium white dwarf or depending upon what is the chemical composition of it. So now we have this blue Stuckler star. We know that they are formed through different channels, but how to really identify them? So to identify them, there are various attempts, and very good attempts were made by UV observations. And the UV observations is because these, if you see, this is a color Manchu diagram. This is V filter versus B minus V, and this is the UV color Manchu diagram where you have NUV versus NU minus optical filter. So what we see in the optical filters is basically these images are dominant from the cooler giants, which are the subgiant or red giant branch. But when we look into the UV plane, what we see that the contribution from the cooler giants are suppressed. So what we get is a clear separation of the blue Stegler star from the sequence, and we can easily resolve these stars even in the central region. So this is why UV sensitivity is very interesting feature to study this star. So a very important contribution was made by AstroSat, and UVIT was one of the 5 payload on board AstroSat. So UVIT is basically a twin telescope. It's a 30 with 38 centimeter diameter, and what we have is it provides a very large field of view of 28 arc minutes, nearly half degrees. So it's quite standard for this cluster kind of studies, and it has a very good angular resolution as well. It 1.2 to 1.5 arc seconds. So even in the central region where the density is very large, it is being able to resolve the stars in the central region as well. So it can combine with the HST and the outer region where HST, since HST has a field of view of nearly 1 arc minute. So after HST, this UVIT is very helpful, and within HST field of view also it is very helpful. So UVIT basically looks into far UV and NUV channel, and these are the wavelengths. And what we are going to do is basically we use this um, AstroSat, UVIT AstroSat, along with other different filters. So this is in UV. UVIT AstroSat helps in UV, but we need that to plot the spectral energy distribution. And what is the spectral energy distribution? Is basically you can consider for a star, this is a black body spectrum. You can consider depending upon the temperature, we have a distribution. For a real star, what happens is from ideal black body, there are some the spectral lines, which is depending upon the chemical composition of that star. We have absorption and emission spectra. So it is not ideal black body, but you have a spectra for a star depending upon its temperature. So what we will do is basically we'll look into different pass bands. So this is from near IR and to FUV. We look at different telescopes, their data. We combine their data sets, and we just take different points and different filters. So what we get is basically we can plot the spectral energy distributions from different data sets, and uh, we can actually uh, fit this with theoretical models, and this was basically used as Castley-Cruz stellar atmospheric models, and we have used VOSA. So VOSA is an online tool to plot the SEDs and to fit it with the theoretical models. So this is very interesting tool. So what we have done is we have used this to identify the binaries in blue stragglers. So basically, with the AstroSat, what we got is we got some interesting binaries that have UV axis. So how this UV axis looks is basically this is a star that is having a white dwarf, the main sequence and a white dwarf. So what we see is this star has a UV axis. So this axis you cannot fit with a single spectrum. So if you try to fit it a spectrum of the main sequence, what you see that this of the spectrum is not fitted well. So and if you try to fit it with the UV part, what you see that the optical infrared cannot be fitted with that. So we need a composite SED to fit the entire spectrum. And in this case, we have used the main sequence and white dwarf to fit the complete spectrum. So one thing, we need multi-wavelength data set from different wavelengths, and for this case we have from far UV to near IR. And second thing is we need to fit the entire spectrum using composite spectral energy distribution. So this is the strategy that we'll follow, and we have discovered a lot of interesting binary systems using this method. So the very first discovery was so this was the paper by Subramaniam et al. 2016, and this is an open cluster, which is NGC 188. So what they have looked is basically they have identified a star that was located in a blue straggler sequence, but when they saw this star has a UV axis. So they tried to look into their SED, and what they found that the UV part is better fitted with a post AGB star, and the optical infrared is fitted with a BSS. So this is the first. You can see that this was the first identification or the first detection of the post AGB plus BSS binary system in open cluster. So I have done this study, the similar kind of a study in globular cluster, and we have been lucky to discover EHB and a BSS binary companion. And this is very interesting because EHBs, people have looked into the binarity in the EHBs, but they haven't found such a system using spectroscopy because spectroscopy is it's a very tedious job. They have to look into various spectra, analyzing a lot of stars. While the photometry, we can actually sample all the stars, a lot of stars at once, and we can actually study more stars in one sample. And with less effort, we can actually obtain the or detect the binaries. So in this cluster, what we have found, there was one star sitting in the outskirts, and this star was found to be a binary, which the optical and IR component was fitted with the BSS, and this was with a EHP, extreme horizontal branch of 28,000 temperatures. And why is it was interesting? Because EHP, to occupy at the extreme end of the HB sequence, the star has to lose a lot of envelope mass during its giant branch evolution. So depending upon the mass loss during giant branch evolution, star occupies location on the horizontal branch sequence. So this blue straggler star is actually helping that with this envelope mass loss. So this explains the origin of EHB stars as well, and also this blue straggler stars, that there's a binary in this system. So this was a very interesting discovery, and this is a very first kind of such system in a globular cluster. Now we have looked into other systems, but a very interesting strategy that we have followed, and that was to look into different BSS sequence, and that happens with a core collapse cluster. So for a normal globular clusters, what we have is basically we have the density which is less in the center region, but when we move toward the center region, what we see, the density increases, but it goes flat at the center region. There's not much change in the density. But for the core collapse cluster, these are more evolved globular clusters. So what we see, that the density keeps on increasing in the center region, and the center is very dense. So because of this core collapse event, that basically as a result of two body relaxation, so what we get is basically two different sequences. And why these two different sequences are important? Because these have two different formation mechanisms. So the one which is related to the core collapse, this is basically related to the collisional sequence. If you actually remember the first slide where I've explained the formation mechanism, so this blue one is basically related to the collisional sequence or merger sequence, and these reds are basically are probable that these stars could be in a binary system. So we just tested it using the SEDs, plotting their SEDs. So we have plotted the SEDs of this blue and red stars. What we found, that for all the blue stars, we have found that the spectra could be fitted with a single SED. But for the red ones, what we have found, that they have a binary companion, and these companions are extremely low mass white dwarfs. So if these extremely low mass white dwarf have a mass of around 0.2 to 0.3 solar masses, so to have such low mass, like for a 12 gigayear globular cluster, so globular cluster have age of 12 to 13 gigayears, what we expect is white dwarf of mass 0.5 solar masses. But to have these extremely low mass white dwarf, they have to have a binary evolution in nature. But these were never detected in globular cluster systems, and this is the first discovery of ELM white dwarfs in globular cluster, and this was in NGC 362. We later looked into this cluster again, and we have looked into another interesting system, and this was the blue lurkers. And what are these blue lurkers, and the difference with the blue stragglers is because the blue stragglers, we know that they occupy a location bluer to the main sequence turnoff here, over some over here. But these blue lurkers occupy their position in the main sequence, but they are in binaries. So we have looked into the 4 of such stars, and for 2 of them we have found that they are low mass white dwarf, and 2 are basically ELM white dwarfs. So this is very interesting that we are able to find some interesting BSS with the white dwarf companions, with the ELM white dwarf companions, and this entire UVIT global survey, which is basically the PI is Professor Anupurni Subramaniam. So Sahu et al. Have basically led this project, and we have published a paper in which we have this is almost 26 globular cluster observed with UVIT globules, and these are globular clusters, galactic globular clusters. So the cyan colors are those which are still in proposal, and red ones which have already been done. And with this, basically, this is the far UV versus far UV minus optical colorimetry diagram. So you can see that we have detected a lot of far UV bright blue straggler stars, the post horizontal branch sequence. This is the white dwarf cooling sequence, and these are the horizontal branch which are bright in far UV actually, and these are some eclipsing some variable systems, RR Lyrae system, eclipsing binaries, SX Finis system, which basically lie in this blue straggler sequence. So we have discovered a lot of interesting peculiar binary pairs, probable peculiar binary pairs, and some interesting far UV bright sources. So these are sources which are very important to look into the SEDs and further look into the discoveries of various peculiar binary pairs. So this UVIT global survey was really successful, but a lot of cluster analysis is still going on, and we are still looking into some of the clusters which are already observed, and we need to take the data and to further analyze it. So this UVIT survey is not limited to globular cluster. They are UVIT survey for open clusters as well, and Professor Anupuni is the PI for that. And there are several students who have worked on it. Dr. Vikrant Jadhav, Anju Panti, and Dr. Sandhu Pandey. And this is these are almost 12 open clusters which are observed through this, and these are the far UV images. So you can see that very few far UV bright sources are there, and this is a part of UVIT that we can actually resolve the very dense. This is the old M67 open cluster, so we are able to resolve in the very central region as well, like for this cluster as well. So this is very so UVIT provides actually the window to resolve the stars throughout the cluster region, and this was very important earlier, because this was not possible earlier, because we have Galax, and Galax has a very poor resolution, which is basically 5 arc seconds. So UVIT was actually helpful in this regards. So this is the color mature diagram. So this is basically these are the color mature diagram of all the 6 clusters and this is for another set of 6 clusters. So this is the HR diagram, and what you see that the various they have also found some various white dwarfs and with different ranges in the masses, like massive white dwarfs, and these are the white dwarf cooling sequences. So in the open cluster survey also, they have identified various binaries, and with the open cluster survey, what they have found is basically interesting is 45% of the blue stragglers, these open clusters are formed through mass transfer channels or through binary evolution. So this was very interesting, because in globular clusters the binary fraction is very low, so that's why the number of BSS those are found in binaries also low. So we have a lesser, like 5 to 10% of the BSS. Those are found in binaries in galactic globular cluster. But in open clusters and in the field region, we got a similar kind of a percentage of the blue straggler stars, which are formed through mass transfer. So this is a study conducted by Anju Panti, and this is in the field region, and you see that they have studied 27. These in the field region, they are called blue metal poor stars. So this is the HR diagram of the field BSS study. So they have detected some interesting system related to the white dwarf companions. Are basically out of 27, 12 are having some hot companions or basically binaries. So with the 6 are the ELM white dwarfs, 12s are 3 are low mass white dwarfs, and 2 are normal white dwarfs, and 1 is high mass white dwarf. So different range of spectrum of white dwarfs they have found as a companion to this blue straggler stars. So this concludes my talk. And with this, so before that, I would like to draw my attention, draw your attention to one of the fond memories, and it dates back to my MSc days when there was an advertisement about this telescope making workshop, which was jointly organized by Vigyan Prasar, Jawaharlal Planetarium, and Aries and Ayuka was also there. So a group of enthusiastic mentors taught us building the telescope from very scratch. So believe me, it was once in a lifetime experience, and the amount of knowledge that we gained practically forever stays with us. And there we met Bharat sir, and you can see from the image, he was among one of the mentors, and he guided throughout the workshop. His inspiration and motivation has always been very encouraging for the young minds like me. And I was in masters those days, so it is a very important part where young minds like me who can plan to choose a career in astronomy and develop their love for the subject. So thank you very much, sir. I owe a lot to you. Thank you. This is all for my talk. Thank you very much. I think if we
Thank
have
you,
any
Gaurav.
questions regarding the talk,
We'll open
so
the question answer session. People have any questions, we can take up. Please, you can one by one. Those people who have questions can raise their hand. So it was really interesting, Gaurav, to understand about the blue stars, and definitely we'd like.
thank you, sir.
I mean, a lot of time when I do conduct stargazing events, a lot of people ask me about the blue stars because a lot of time we refer easily the red stars, yellow stars, white stars, you know. But people ask me about when colors comes, people are very enthusiastic about talking about different colors. So, sir, is there any green star or blue star kind of thing?
Yes, yes.
Anybody has any question? So there are questions which has been come to me on the chat also. So I'll meanwhile put that questions to you. So as you said that we are more prominently blue stragglers are into the globular clusters, but you have talked in your talk also about the open clusters. So what is the distribution like from globular cluster to open cluster? Do we have more number of blue stragglers in globular clusters and less in open clusters, or how?
So in terms of numbers, the globular clusters, in general, their numbers are large. The globular clusters, if you talk about the number of stars in globular clusters, so they are 10 to the power 5 stars or 10 to the power 6 stars. And while for open clusters, if you talk about the number of stars, those are 1,000 to 10,000 of them. So there's a number difference in these kind of star clusters. But if you talk about the blue stragglers, so the number of blue stragglers, those are basically similar in numbers, and this is because the binary in the basically some old open clusters, their binaries are basically the binary fraction are large, 50% of them. So the binary fraction is large. So mass transfer blue stragglers are similar in numbers, but those which are formed through collision, basically in the central regions, those are large. So globular clusters have in conclusion, globular cluster has larger number of blue stragglers, but the binaries containing the blue stragglers, those are same in numbers in both the globular cluster and open clusters.
Okay, thank you. We have a question from Prashant Banerjee. Can UVIT resolve closed binary blue stragglers in very dense cores of globular clusters, or are higher resolution tools like HST still required for such detectors?
So, if we avoid the central core of the globular cluster, after the core, still in the it comes in the HST field of view. So we can resolve these binary stars, and we have conducted the study within the HST field, but we have avoided the core region. So we can resolve in the center, but the core is very dense. So even with UVIT, we cannot resolve. We need HST for that region. Yes.
Okay, Bharat sir, you have raised your question. Bharat sir, Bharat sir, you are on mute. Uh, by the time Bharat sir comes online, we have another question from Umesh. Can blue straggler star exist outside of the star cluster? And if so, how could we distinguish them in a galactic field?
Yes, so basically, yes, during the cluster evolution, these field blue stragglers are basically kicked out of the star cluster system through this two-body relaxation process. But how to distinguish with the one that are found in the star cluster system with that of the field? So the field blue stragglers are mainly found in the binaries, where those in the cluster systems are like in open cluster system they are found in binaries, but in globular cluster they are mainly in the collisional or through the single stars. So this is the only distinction. But if you look into the mass transfer formation of those the field and the cluster one, there's not much difference in the spectroscopy and other chemical abundances. So this is basically the similar kind of a features that we look.
Okay, okay. Connection with the first question, what I asked from the participant, there is a related to that same. Do all star clusters have a blue straggler stars, and do these blue stars live longer than the normal stars?
So do all star clusters? So answer is no. The young star clusters do not possess this blue straggler star, because for these blue straggler star it needs some million years of time, either through collision or through mass transfer. It needs some time. So the stars clusters which are like in open clusters, the young clusters with the age of less than 2 million years or 3 million years, they don't possess blue straggler stars. So the this is I can say about that. Yes.
And do the blue star live longer than the normal stars? How is their life cycle or the sequence? How do they end? I mean, do they follow the same sequence or they do live longer than the normal star?
Okay. So yes. So I think this is an interesting question. Um, I will just talk about this thing. Yes. So if we talk about these blue straggler stars, do they live longer? Yes, they live longer because they still manage to burn hydrogen in the centers. So of course, other get evolved. These still manage, but they also evolved, and they evolved towards the sequence. Their sequence is now, so the turn off is for these normal stars is for here, but for them it turn out. So the turn off becomes like this. So they evolve like this, and they further get evolved towards the. And so these basically are called evolved blue stragglers, EBSS. So yes, they evolved, and the EBSS studies are also there. So they basically lie somewhere near the this AGB starts of the AGB sequence actually.
Okay. Anybody else has any questions to take up? Bharat sir, you want to say something? Are you in position? I think Bharat sir has some problem with the hearing, so that's why he's not
Okay.
speaking.
I
Uh,
think Bharat sir, you can put your question in the chat box.
yeah,
That will be
I
helpful.
think there is one more question from Souvik Mukherjee. Is there any chance that the blue straggler stars becomes black hole after certain amount of mass transfer? If that's what is the limit of that?
Yes, so for black holes, it needs a mass of around 8 solar masses. So blue straggler star can maximum go up to 2 to 3 solar masses. They cannot go that much for to go towards the black hole or that kind of a system or neutron star. So these are basically the maximum heavier blue straggler star is basically found to have 3 solar masses. So their range is around mass range is around 1.2 to 3 solar masses. This is the only range, either from either of the channels. Even for the triple systems, this is the heaviest blue straggler star 3 found. So in principle, no.
Okay. Anybody else? Bharat sir, I think you are now, you can speak.
Yeah, I had a small question. This is regarding after 53, 1953, after the Sand Age, and and talked about blue stragglers. Uh, has there been any evaluation work happened on these blue stragglers? I would like to know more from Gaurav, Dr. Gaurav.
So the evolution of blue stragglers.
Should I repeat?
Sorry, sir, I couldn't. Yeah, yeah, sure.
Yeah, I'm saying since the first observation were by Alan Sandage, and
Yeah.
thereafter, has there been any specific stellar evolution done on these blue stragglers? And I saw your curves for these blue stragglers, but what is the outcome after they finish their uh, part in the evolution? How do they end up? This is my question.
Okay, sir. So blue stragglers, after they evolve, they basically takes the position of like they evolved as a heavier mass star. Like if you see for a blue straggler star, so normal cluster star turnoff is around zero point 0.8 solar masses, but these blue straggler star, let's suppose 1.2 to 3 solar masses. So they have the similar fate of what the massive stars have. But this is being delayed. For the massive stars, it's evolved quickly. But in this case, these are massive, but they evolved late. And this is still when this process, this mass transfer and the collisional process actually allow them to stay at this position. So this has the similar fate, but they still manage to stay at. So this is like a traffic jam where you have a signal and you're waiting for the signal to open. So once that process happen, it just move in the similar fate like a massive star.
Okay.
Dr. Gaurav, I have two questions for you from one of the participants. So, what clues do astronomers look for to find in blue stragglers? I mean, and second thing, any normal stars what we see in the sky can be identified as a blue stragglers. Like, notably observable any of the stars which you can refer as. That's the curiosity question from
Well,
quickly.
yeah. So looking at this blue straggler star from normal eye, I don't think that it could be like they are just in. I'm talking in terms of this main sequence turn off. So they're relatively brighter. They are not very much difference that could. I couldn't get the first question properly. So could you repeat that? The first part.
First question was what clues do astronomers look for to find in a blue stragglers? I mean, what are the things we like to learn more from the blue stragglers?
Yes. So basically, so as I said that their existence itself was debatable. That how we could have stars which actually challenges the canonical stellar evolution. So this was the first thing that that puzzled astronomers to look into them. The other things are related to what are actually the different formation scenarios if this is mass transfer. So there are different types of mass transfer, like the star, the other star gets into white dwarfs. So the donor star could be different masses. For one donor star could be a red giant or a subgiant branch. For one donor star could be a asymptotic giant branch. So there are different cases of mass transfer in these kind of blue straggler stars. So to understand that what are different companions we get for the blue stragglers to evolve. And the second thing is uh, related to um, the different studies in different clusters to really understand that what are their ages, their typical evolution. So this is what one can do with the blue straggler stars and study them.
Okay, and that second question, what we asked about, whether we can see it through the naked eye. Is it possible also to see probably through the telescope or even through telescope? What kind of telescope? I mean, it is what limit what we can use, or it is only about
So
or something like that only is required to see this.
So I think with the normal eye, I don't think that it is very significant to distinguish with the normal eye. But yes, with the telescope, we can actually do this very simple exercise of plotting the HR diagram. We can confirm this using the HR diagram only. But with the normal eye, I am not sure whether you can actually distinguish blue straggler from a normal star, because here we are talking only in relative terms, so they are relatively brighter, not very significantly brighter, so to observe from the normal eye.
Okay, okay, thank you. Anybody else has any question? I think Sudhindrita Pandey has, why are blue stragglers often found in the cores of the cluster? And even Umesh
So
has,
why they are found in the cores of the cluster?
yeah, why are
Yeah.
the blue stragglers often found
So
in the cores of a cluster?
yes, so I think as I said that the core is, this is because the gravitational interactions. So the more you have interactions, so as I said that they are formed through a process that needs the interactions. So these gravitational interactions are actually forcing them to either collide, or since they are dense, so we have a binary system as well. But the cores of the globular cluster, where gravitational interactions are very probable, there you can have um, uh, blue stragglers form through this collisional systems, or this merger systems basically. So that's why they are very found in the cores of the globular clusters.
Okay, thank you. And Umesh has put one question: can time domain surveys like GIA or TSS helps in detect eclipsing binaries or pulsation in blue straggler population?
Yes, so this is very interesting. So people have studied from tests, observations, and test provides a more insightful way into the eclipsing binary systems, like those which are in the eclipsing. So they provide actually the orbit. What could be the possible orbit of those, and what are the period, what are the different nature. So yes, for the eclipsing binary system, the test observations are very insightful, and they provide more details into that. With Gaia, Gaia really helps in the proper motion to select that whether they are actually cluster members or not. With the proper motion, we use that, and I hope the proper motion is slightly difficult topic, but yeah, you can understand it like we like for a cluster, since they are gravitationally bound, they move in a bulk, so they have some bulk motion. But the field stars, either they are foreground or background, so their motion is random, so there's internal dispersion is large. So in the proper motion plane, what we see is basically the cluster stars to be segregated, while the field star to be dispersed. So that's how we select these from the Gaia using proper motion. So Gaia helps in those terms.
Okay. Anybody has any other question? Bharat sir, you want to add anything? No?
The we one of the things which I had in order asking Dr. Gaurav to take up this topic was primarily because we should be also aware of the subject which is now coming up with different kinds of forms which are coming. There should be more observations taken up with uh, these kind of observations are necessary for astronomy. So it is my
Yes.
humble request to all the participants who are here that it, one mission is not sufficient. And I requested even Dr. Gaurav to think about a satellite to look for ultraviolet stars, not necessarily for as blue stragglers, but uh, blue stars if they are blue stragglers overall in the whole of our Milky Way. So
Yeah.
his talk was excellent. I have been following it, but I'm sorry, I have a little ear problem today. So I
Okay.
am
Okay.
now just suggesting that you should now look forward beyond postdoc is to put up a UV satellite. So it is our request we should not limit ourselves only to X-rays and this. It should be much beyond the spectra at UV
Sir,
level because
for
whatever
this,
support
I
is
would like to,
required, definitely
yeah.
we have members here who can really guide us further. So I again, once again, thank Mr. Gaurav for accepting our thank you.
Thank you,
Yeah,
sir.
Gaurav,
I
you want
think
to
to
add
add
something?
to this, I would say that I'm working on the current postdoc. In my current postdoc, I'm working on a UV telescope that is on the lunar surface. So the lunar surface, since there is no atmosphere there, so it's a robotic telescope on Changi 3 mission. So basically, Changi 3 is a very similar to what we have a Chandrayaan 3 mission. So soft landing, and the it was the first soft landing from Chinese space agency. So they put up a telescope, and so we should think of putting the telescope on the surface of the moon. I would love to contribute to that.
Okay, okay. Thank you, Gaurav. With that, I think if we have any other question, we can take up or we can conclude. Anybody has any further questions to talk or ask? Feel free to ask, or we can conclude today's session. So, Dr. Gaurav Singh, today's session was very great, and definitely this is another type of the stars what we learned about and came to know about it more in detail from your study of research. A big thank you to all of you as well as Mr. Gaurav for helping us to explore the wonder of stars and mysteries of blue straggler stars. There could be a lot of questions further comes up. I would put you on the chat or in the WhatsApp,
Sure.
and let's look forward for more to hear you in near future on your research. And as you said that you are trying to put up Changi 3 setup and where you will able to observe the moon lunar surface in UV. With that, thank you very much. Thanks everybody for joining today's session and listening patiently for to our speaker. Thank you, Bharat sir. Thank you everyone once again for today's session. Thank you.
Thank you, Mangesh sir. Thank you, Bharat sir, and everyone for listening to my talk.